Good morning, good afternoon, everyone. We'll give everyone a few more minutes to get into their Zoom accounts and log in. And then Dr. Jim Rickles from Lehigh University will give an introduction to our seminar speaker for today. Okay, we will start in 1 minute. As a reminder to anyone that's participating, please save your questions for the end of the seminar and we will address everyone. You can either raise your hand using the participant window in the Zoom, or if you are on mobile, you could, or if you're on a desktop, you could type in the chat box. We will look at questions in both ways. I'm going to hand this over to Dr. Jim Rickles now for him to give an introduction to our speaker for today.
Okay, good afternoon, or maybe good morning, everyone. This is Professor Jim Rickles. I'm the director of the LEHIGH NERI experimental facility. Hopefully everyone can hear me okay. Tommy, you can hear me okay?
Yes, you're coming through clear.
Okay, so I wanted to welcome everyone to the LEHIGH seminar series from the NERI site. This will be one of several seminars we'll have on an average of one a month. I'd like to welcome our speaker, Maria. That's abbreviated for her first name, Professor Maria Soto from the University of Kentucky. She specializes in active and semi-active control, and should be talking about multi-agent replicator control methodologies for sustainable vibration control of smart buildings and bridge structures. I'd like to note that the Q&A will have Q&A towards the end of the presentation, and I need to ask my organizer here, do we do this by raised hand, Tommy, or people will just ask a question by unmuting?
We will have them raise their hands or ask in the group chat, either way, and then we'll unmute those people and I'll call them out by name.
Okay, and what I'll ask everyone to do, except of course for our speaker, is if you can mute your microphone, because otherwise sometimes it generates background noise. And so with that, welcome, Maria. We appreciate you presenting your research. We'll hand everything over to you then.
And you could share your screen at any time.
Okay. Well, good afternoon, everyone from Lexington, Kentucky. Let's see. Oh. Sorry, I don't know why it's not showing. Can everybody, are you able to see the screen with the presentation?
We can see.
Thank you. I am very excited to be part of this seminar series by the Natural Hazards Engineering Research Infrastructure. And today I'm going to be discussing my research on multi-agent replicator control methodologies for sustainable vibration control of smart building and bridge structures. So a little bit of the overview of what I'm going to be discussing today. is 4 parts. The first part introduces the multi-agent replicator controller, or MARC, that integrates 3 multidisciplinary concepts. Then we're going to go to part 2, which is the multi-objective control optimization that is using a neural dynamic model, which is bio-inspired. And we're going to look at 2 very interesting applications, one using a smart base isolated irregular buildings and also highway bridge structures. So let's begin. So part of the motivation is to make sure we look at smart ways to mitigate natural disasters. This is one example from the Nepal earthquake. And protection of infrastructure is very important, especially with all the events that we have seen lately in this year. So looking at the distribution of the disaster impacts is very uneven, and especially in lesser developed countries, but it's also very important in developed countries because it provides an economic loss, especially in terms of recovery from natural disasters. So with that, we going into the introduction of what is control engineering. So broadly speaking, is a field in which a dynamic system, you're trying to regulate certain variables of the system, which is commonly used or seen in robotics, autonomous vehicles, space flights, smart cities, and also in smart civil structures, which we're going to be focusing today. So what are the paths leading towards intelligent structural control? This could be subdivided into passive control, semi-active control, and active control. So a conventional structure would look something like this, where you have an excitation, and you have the structure, and then you're measuring the response of the structure. When we look at passive control, you're basically adding a device into the structure. And this stands for passive energy dissipator. One example of this is a tune mass damper. A tune mass damper is a device mounted in structures to reduce the amplitude of mechanical vibrations. Their application can prevent discomfort, damage, or even structural failures. Practical systems are tuned to either move to the main mode away from the troubling excitation frequency, or to add damping to the resonance that is difficult to damp directly. This is one example, which is Taipei 101, located in Taiwan, and it's a pendulum tune mass damper. As you can see, there's a huge wall over here that is between the 87th and the 92th floor, and it's suspended by cables. This sways is done so that it offsets the movement in the building caused by strong gusts, and it's also being able to withstand the typhoons that recently happened a couple of years ago. This is another example. This one is located in Japan, which is the Crystal Tower. So instead of having the mass being out of steel, this one is actually an ice thermal storage tank, which is actually freezing water, suspended also by cables. So if you look at the top right, we can see 4 of them over here, and it's swaying in one direction, while these other 2 are swaying in the opposite direction. Another example is also the tune liquid column dampers. In this case, we're using water. And what happens is that the building is moving in one direction, the water is swaying in the opposite direction, which creates that counter movement. The idea is that you're able to determine the size of the orifice so that you can tune it also to reduce the vibrations in the structure. The tune liquid column damper is named like that because you have an U shape. Now let's look at the next example. Another way of doing passive control is the additional of fluid and friction dampers. Some can be seen here as cross bracing, as well as in this other example for real life applications. Now let's move into active control. Now, not only we have installed actuator devices, these are able to act in real time. In order for that to happen, you're measuring the response from the structure through the sensors, and this information is going into the controller. which is basically the brain of the system. That's why it's considered intelligent or smart, because they're able to think and react in certain ways. The controller then determines how many forces or how your actuator is going to move. And that's where it comes. One real-life example is the Kajima Shizuoka building, which is a semi-active hydraulic damper. As you see here, you have the bracing, but you also have this hydraulic damper connected to it. You have sensors installed in the structure. They're giving information to the control computer here, which also has a backup generator so that you don't have interrupted power supply during an earthquake. So leading to the intelligent control algorithms, so what's inside the brain of the computer, we have several different examples as my experience working in the knowledge engineering lab. So the first integration to control optimization in structures was done in 1994. You use the wavelet-based control algorithm, which is the integration of wavelets in order to reduce the noise. We have also worked on high-rise building structures where they have geometrical and material nonlinearities and how to come up with a control algorithms that can move into that particular constraints. We also work on self-constructing wavelet neural network algorithm, which is basically the combination of different self-computing algorithms in order to control the structure against natural disasters. And also linear matrix inequalities. So let's move to the first part, which is a multi-agent replicator controller for sustainable vibration control of structures. So again, we're gonna be combining three different concepts: decentralized control, agent-based modeling, and replicator dynamics. So in a centralized control, you basically have one controller that is basically making all the decisions. The sensors are capturing information, they're sending it to the controller, and the controller is making the commands to the actuators to move in a certain way. Sorry about that. In a decentralized configuration, you can divide the structure into subsystems, and each of the subsystems will make decisions based on the localized information. Now, in this example, we have two different controllers, and they are communicating with each other what's in the interface between the subsystems. So you can see that you have the structure divided into two. Some of the advantages for the decentralized control system is because it provides robustness and reliability in case one of them fails. Additionally, because you are in a distributed computing environment, you can make decisions faster. So it reduces the computational efficiency constraint. And it also, it's been proven to have reduced energy requirements. So the second concept we're going to be using today is an agent, which is coming from the artificial intelligence community. And it's basically anything that can be viewed as perceiving its environment through sensors and acting upon that environment. One of the key things is that your information that you're perceiving from the environment allows you to make decisions in real time. When we integrate this into Replicator, into our problem, we're basically using information from the environment and what decisions are going to be made. So the agent has to think and be able to come up with a way to react, right? And the way we're going to be using that reasoning is using the concept of replicator dynamics, which is going to be instructing the actuators to move in certain ways. Now, the third concept that we're going to be talking today is evolutionary game theory, which is basically the study of mathematical models of conflict and cooperation between intelligent, rational decision makers. One of such concepts in game theory is the replicator dynamics. Replicator dynamics is basically a concept which is inspired from biology, and it models how natural selection affects a population. This can also be known as the models for imitation, which replicates a successful strategy. So let's look at a little bit of an example. If you see someone who's rich or famous, and you also want to be rich and famous, then you want to replicate those decisions that they're making so you can also be successful and rich. That's why the name comes with replicator, because you're replicating a certain strategy. So let's look at this example. We have the total population. Let's suppose we have three rooms, okay? And we're trying to control the temperature. then one of the rooms is cold, another room has a slightly warmer, and the other one is just in neutral. Now, what happens is that you are distributing the resources between these three rooms. If you want one of the rooms to be slightly colder, then you want those resources to be given to that particular room, while the other ones may remain the same. And those resources that were given to room number 2 are given to room number 1, so they can use those resources efficiently because this room already has a temperature that is ideal. Another way to look at it is that, that we want to make sure it's mentioned here, is that the population, so the total available resources, remains the same. So the population has not changed. It's just the distribution of the population is the one that is changing. In our particular example, we're going to be looking at the emergency power generator, or the total available resources for our structural control, to be distributed between these different environments. But the maximum remains the same, which is the total population. Now, how does this all come together for structural control? So the first thing we have to do is gather information from the structure and determine how many substructures are we going to be using in this particular device. Once we determine how many substructures or how are we setting up the structure, then we're going to determine how many actuators and sensors you want each substructure. Once that is done, then you create a control agent, which is going to be for each substructure. Each of the substructures with an agent will be making the decisions using Replicator Dynamics. Now, Replicator Dynamics has key parameters in order for distribute those resources among all those population habitats. And that's going to be the total actuator forces on each subsystem. You have the initial conditions and also the growth rate. Once we satisfy the performance criteria, then your multi-agent replicator controller is set to go. Let's look at it a little bit closer. So we have a structure, and we want to subdivide this into 3 subsystems. Each of the subsystems will have an output, and each subsystem is communicating with the adjacent subsystem, as you can see here. Each of the subsystems will look like this. So you have information coming from the interface, so from the other subsystems. You also have the external excitations, and you also have the output measurement. So inside that subsystem, it looks like this, which is a feedback loop. You basically have information from your plant, which is your structure, and you also have the control agent, right? So you're taking measurements from the sensors, either displacement or acceleration, for example, and you're giving that information to the control agent, which in turn makes the decisions on how the actuator forces are going to act in that particular time step. So when we look at this, what's inside the control agent, this is what's happening inside. So you have all the measurements that are coming from the structure, and each of the actuators will have a set fitness function. You also have a fictitious floor, which I'm going to talk about briefly. And this one is the parameters that are for the replicator dynamics to work. So again, the total resources are going to be the total amount of forces in the system. You also have the growth rate. Those are the 2 main parameters for the replicator dynamics. Now, what is this concept of fictitious floor? The fictitious floor is basically the player that's always winning. So like I mentioned before, in replicator dynamics, you're trying to replicate a successful individual agent. In this case, it will be this fictitious floor. So he's always winning, and everybody's trying to replicate whatever it is that he's doing in order to win. Once this dynamic is in place here, then it's determining what the actuator force are going to be in that subsystem. Now, let's look at the equations on the replicator dynamics. So you have this term right here, which is the average fitness function. So for this particular device, he's looking at his fitness function with respect to the average. So this right here is going to determine how the resources are going to be distributed, okay? So if for some reason I'm above the average, that means that I need more resources in order to achieve the goal. In the opposite case, if you're below the average, then you can let go of some of those resources. That way we are going to be achieving a sustainable design. As you can see here, it's a weighted average. So you're multiplying the amount of forces times the fitness function. the fitness function is quite important. So we devise basically the following. So the fitness function is going to be the maximum between my current displacement, for example, and my desired displacement. Or it can also be my current velocity with respect to my desired velocity, or acceleration. So what is my acceleration right now with respect to 0, for example? So if we are comparing drift, for example, you can also put that as your fitness function, or maybe a combination. The reason why we have two is because part of the replicator dynamics has to be positive. Like the fitness function has to be positive. But because we're looking at structural design, some of the measurements are going to be negative, right? When your displacement is negative or your velocity is negative, then this is how we're going to manage that design. Now, let's look a little bit more into this. Looking at the pie chart when time equals 0. So we have an equal distribution of resources among all of them. So this represents the resources allocated to actuator 4, or the amount of forces given to actuator 4 at that time. And this one right here in particular is that fictitious actuator, okay? And the summation of all of this is the population, which is the total available resources that are gonna be distributed among all these floors. So for floor 1, for example, we take the state measurements, we take it here, and then this is the fitness function. So we're looking at what that particular measurement is with respect to my desired one. And then that's taken here into this average fitness equation. Then we look at what we have right now. And as you can see, when at different time steps, the resources are distributed differently depending on where you are. So this one changed and increased the number of resources available to that floor versus the second floor. So this is how the replicator dynamics takes place at every single time step. Now we're gonna look at a proof of concept. So the first thing we did is look at the 3-story steel frame. And then we subjected it to 4 different major earthquakes: Kobe, Central, Hachinohe, and Northridge. Now, what we noticed is that those 2 key parameters that we discussed, so the total available resources, which is the total available forces, and the growth rate, those are the key parameters for the replicator dynamics. So at every time step, we change those values and see how it behaves. What we notice is that the values, depending on which earthquake, change, but they all have interesting characteristics. So let's look at the flat representation of this particular plot. So if you wanted to improve, you basically want to be on this area. And the values that you want to choose are going to be here, right? So that's simple enough. You pick a value for growth rate here, and then the population here. The reason why I'm pointing at this particular location is because that one means that you required less energy in order to perform similar to the other competitive values. Now, CRC stands for Centralized Replicator Controller. So that's when you have one computer making the decisions for all of them. In the multi-agent replicator controller, you have the decentralized configuration with the interface communication. And what we see here, that during the same earthquake, when we look at the optimal parameters, we notice that Mark uses a lot less energy than when we look at the centralized comparison. So Mark is definitely a lot better in terms of like finding out what these optimal values are. This is the time history analysis. So we're looking at the maximum displacement, and we're comparing it with LQR and decentralized LQR, which are conventional control algorithms that stands for linear quadratic regulator. So in order to compare these different control algorithms, we basically set the maximum control force to be sort of equal to each other, like the maximum capacity. And then we look at the performance, and we can see that our proposed one was able to perform better than the conventional ones. Now, when we look at maximum acceleration, we also notice a similar thing. So this is the uncontrolled one, and the green and pink represents the conventional one, and ours is also able to also reduce maximum acceleration. This is the interstory drift. So this is one of the key values that we're trying to reduce for earthquake design. And we can see that all of the control algorithms was able to reduce, the vibrations, but our proposed one was able to really effectively do that. So we move into the American Society of Civil Engineers 20-story benchmark example. This particular example has been designed to provide a control algorithm comparison. So this is available to test different control algorithms. And the other thing is that this one was designed for the seismic code in Los Angeles, California. So it's a particular good example to test our proposed algorithms. The other thing that we talked about before is that we saw that there was a different optimal values for the replicator dynamics when we look at 4 different historical earthquakes. So in order for us to evaluate the performance, what we want to do is actually test it for thousands of earthquakes so we can have the best possible solution. So what we use for create artificial accelerograms is using the Kanai-Tajimi model. And this is just one example where we have the Kobe historical earthquakes, and this is the artificial one. So we're able to replicate fairly well in terms of PGA, so the peak ground acceleration. The other thing that is very particular about this Kanai-Tajimi model is that you have the ground frequency as well as the damping ratio and the amplitude. So this particular variable, you're able to compare it using soil characteristics. So if you have soft soil or hard soil, then there are particular values that you can use to represent that. So these are just samples. And as we are changing the values of the ground frequency, then we can see how the maximum is changing or how the behavior of the earthquake is changing. So this is how we're gonna be testing our multi-agent replicator controller. Now, when we use 500 earthquakes, we're gonna determine what will be the best value for growth rate for a particular set. And we can see that when we use velocity feedback for the ground frequency, so for the soils that are in this particular range, then the value will be closer to this. But when we look at other soil characteristics with harder soil, then the best value for growth rate would actually be averaging over here. Now, when we tested it for acceleration feedback, so that's when we actually use sensors to capture acceleration of the structure, then we actually see a better performance for the replicator dynamics in terms of what will be the best values for growth rate and for each ground frequency. This is basically another comparison of our proposed methodologies. So CRC and MARC have the force in terms, and then we're looking at the time history for displacement and acceleration, and we can see that ours are performing quite well. In terms of interstory drift, then we can see that the uncontrolled and comparing it with the pink and red lines, those are the conventional control algorithms. And then we see something really interesting about when we look at MARC and CRC. So we can see here that CRC is basically distributing all the resources basically to the top, while MARC is able to distribute them more evenly. Now, a lot of this work was done using sensitivity analysis, which is very time consuming, especially when you're doing 2,500 earthquakes. Now, if we look at many objective control optimizations, then we're able to achieve another type of result. So just to look at multi-objective optimization, it's when you have competitive objectives. So let's suppose you're trying to minimize one objective, and then we have the second objective, right? So the best value to minimize the objective number 2 will be here, but to minimize objective number 1, the best value will be here. Now you have 2 competitive values that you're trying to choose from. So then you create this Pareto front so that you can get like a compromise between those different objectives. When competitive objectives that you're trying to minimize or maximize, then you create a surface and so on. So the multi-objective optimization that we're gonna be using for our particular problem is minimizing the floor accelerations. Then we're also gonna be trying to minimize the interstory drift. And the third one is going to be the P, which is population, which is the total available resources. So this is gonna be the third value, which is the sustainable purposes. So using less energy to achieve good performance. The other thing that we want to look at is because we have 3 different objectives and we want to make sure that there's no undue dominance. So we are going to put some priority on making sure we reduce acceleration, second, drift, and last, the energy, because we want to make sure we protect the structure. Is to determine what will be the best replicator parameters. So some of the constraints are basically the maximum actuator force. We also have designated interstory drift limits, and we're also going to regulate the maximum values for the growth rate. When we look at the neural dynamic model of a delaying park, it has been used to really work well with kinky constraints and also for nonlinear problems. So this is why we're using it. What we're gonna look here is a time step. So we have here the different objectives that we're trying to minimize and also the constraints. So these are the equality and inequality constraints. We're also looking at the Lagrange function. So what this does is we have a penalty function. So for every time step, you wanna make sure that it's increasing in time so that you place more importance on the constraints and you're not stuck on a local minima. So when we look at the Lyapunov stability theorem, then we're looking at how we're gonna minimize this in every time step. And this is solved using the Runge-Kate method, which the equilibrium point will be solved using numerical integration of the fourth order. Now this will look like this. So this is the topology for the neural dynamics model, because at every time step is learning more about how the system behaves. We're gonna be optimizing the control variables, which is P, and we're also gonna be looking at optimizing not only just one value for the growth rate, but the number of devices that you're trying to, that you're gonna be working with. So if you have 100 devices or 10 devices, then that will be 10 different replicator dynamic parameters, and also the fictitious actuator. So let's look at the same, applying this optimization algorithm using the ASE 20-story benchmark. So looking at the performance, we can see that for F2, which is the drift that we're trying to minimize, the values decrease when we're working on higher amplitude earthquakes. And we can see that we're trying to minimize the values. Oh, I guess I didn't put the other graph. But for, so this is also the results for every time step. So if we're looking at the number of iterations on the neural dynamic model, for each time step, the objective functions are going down, which is what we want. We want to decrease the acceleration of every floor, the drift, and also the power that you're using in order to solve that. When we see these type of jumps, it means that while we're decreasing this one and this one, then when you reduce the total available forces, then you're actually gonna have an increase in performance. And then the neural dynamic understands that that's not what we want, so that it goes back down. This is how the variations of the growth rate parameters. So from the initial conditions, then we can see how each of the parameters change with respect to each iteration in order to determine what will be the optimal values for each one. When we test the values that we chosen with the Kobe earthquake, then we can see that the performance of the neurodynamic model is working really well, especially for CRC. And so both of them were able to reduce the response with respect to the uncontrolled performance. Then going to the third part, we're gonna look at how we implement this kind of strategies for smart base isolated irregular buildings. What does this mean? So base isolated structures basically have this isolation bearing, and it's fairly common in earthquake areas where you have this rubber bearing dampings or elastomeric or friction. You have so many, and the idea is that you're basically isolating the top structure from the earth, and it's basically doing that deformation that prevents the structure to displace, like allowing that kind of flexibility. Now we want to prevent that it deforms beyond the plastic limit or something like that, and then we can add a control device to this that will be able to help make sure that this is adaptive. So the idea is that you're combining two different type of control control algorithms. You have the passive control, and you also have the semi-active or active control. You're taking measurements from the structure, you give it to the computer, and then that's going to give in the instructions to the control or the actuator. Now, why irregular structures? Because you also have torsional vibrations. A lot of times, irregular structures are not very studied often. So we're going to look at if we have something that can adapt and to not only reduce translation, but also torsional motions. So this is how the replicator will look like. Now, the main difference is that instead of having actuators on every floor like we had before, we're going to have it in the plan view. And because this is a three-dimensional building, then we're going to have actuators in the X and in the Y direction. So for the measurements that are positive, this is one way of looking at it. So the fitness for the X direction, we also have the Y direction, we also have the fictitious actuator. When we look at how this all comes together, we have also the same average function that is going to be given at each of these replicators, and then that is going to be determining what these actuator forces are going to be, and then it's going to be given to here. This right here represents another entire replicator dynamics that is taking place, but for the measurements on the negative direction. So what happens is that when you have positive and negative, then that's going to be determining like either 0, right? And then the other one will be positive, and it's going to determine the direction in which you want the actuators to move. Now we're going to be using also the neurodynamic model in order to obtain what these optimal parameters would be. And this will be the betas in the X direction, as well as the growth rate in the Y direction. Also for the fictitious actuator, actually, excuse me, and also the population, so the total available resources. The objective functions in our case will be reducing the acceleration in the X and the Y direction, as well as the bearing deformation. Oh, sorry about that. And lastly, our third will be to make sure that we're using the minimum possible energy. So we are going to put some emphasis on the first two measurements, and then lastly, the third one. So this is the example. This is also a benchmark control problem. This one has a combination of elastomeric bearings as well as 16 actuators. In this configuration, we're going to try to control to make sure that these ones are moving in real time and reduce the vibrations. So we're going to be testing it to all these different historical earthquakes. And this is what happens. So when we look at Pareto optimality, we're looking, okay, so we want to make sure that we don't overstrain our actuator, so we have a maximum control force. And then we're also trying to improve the performance criteria. So we can see that certain values, you're going to have interesting performances. So because you want to make sure you remain below the maximum limit, but you're also trying to reduce the performance. So you can see there is our competitive objectives. So when we look at the 9 different criteria, this is what we're looking at per number of iterations. So as the neurodynamic model is moving in real time, we can see that the improvement on performance. The criteria 6 is actually the control effort and also the energy being absorbed by the system. So we actually do want to make sure that those are increasing, because it means that we're performing better in terms of capturing that vibration. So these are how the values are. Let's say the constraint variables that we're trying to optimize. So the growth rate values as well as the total available resources. And this is the comparison. So we have Northridge and Kobe earthquakes as some of the sample results. And because this is an irregular structure, these are basically the floor displacements, okay? And we're also looking at the rotational, so torsion, right? So we can see that not only are we able to reduce the vibration, but when compared to the LQG, which is the conventional one, we can see that we're able to improve in terms of the dampening of that. Now, the last example that I'm gonna be briefly discussing for time is the semi-active vibration control for smart isolated bridge structures. So this is looking at a hybrid control as well, because we're going to be combining isolation bearings with actuators. So in this particular case, this will be a close-up of what is inside the west abutment. This is actually inspired so from an actual bridge that we're going to be looking at later. So right here, this is how the replicator dynamics will work for bridge structures. So we're going to be taking measurements, and in this case, we're using semi-active control. So some of the sensor measurements actually are going to be given to the control device. This is given to the control agent. It's going to be taking the measurements. Then it's going to be going through the fitness functions, and the replicator dynamics in this case are going to be given voltage supply to the semi-active control devices instead of forces like we did before. And again, these are going to be dominated by these three criteria. So the total resources, the growth rate, and the fictitious device. So again, we have one device that is going to be the ones that everybody wants to replicate. So this is actually a bridge located in California, and it's based on a case study. So this one has been instrumented, but these are passive devices. So these ones are passive hydraulic dampers. And because this has been studied, we can look at how if we replace these devices with semi-active control, then that will actually look at it, can we actually improve the response from it, right? This is the cross-section of what it looks like, the center bend. And then we can also see the elevation view of the highway. This is how the plan view, so we can see how it's instrumented. It has 4 different isolation bearings here, 4 here, and we also have 2 here. And we also have actuators. Those are the ones that we're gonna be devising. So what we did is we did a sensitivity analysis comparing the total population with the growth rate. So we're looking also at minimizing the overturning moment, mid-span displacement, and also mid-span acceleration. So we have about 16 different criteria that you're trying to minimize, and we're looking at what will be the optimal replicator dynamic parameters to get the best performance. So we can see that around this area, those will be the best minimizing parameters in terms of total population and growth rate. And then what we did here is that we compare with the 6 different earthquakes, and we look at what will be the best possible value for population as well as growth rate. What this means is that some of the earthquakes actually are not as strong, so you don't need that much control, like available resources to control it. So these are the comparison between the mid-span displacements in the X direction and also in the Y direction. And we're comparing it with all other semi-active control parameters and the passive control when you only have the elastomeric bearings. And to conclude the presentation, we have 3 concepts that we integrated. So decentralized control, agent-based modeling, and evolutionary game theory. We combine them to reduce vibration of the structure and also achieve an energy efficiency compared to other control algorithms. So we actually developed 2 different control methodologies. So it's the centralized replicator control and also the multi-agent replicator controller. Because of the way we have to determine these replicator parameters, we implemented a many objective optimization in order to obtain this Pareto optimal replicator control parameters using a patented model for optimization. And we were able to evaluate these proposed control methodologies using low-rise and high-rise regular structures, as well as 3-dimensional base isolated regular structures, and also highway bridge structures. Part of the future research is integrating this and validating these control methodologies using real-time hybrid simulation. And we're looking at LEHIGH University as part of one of those possibilities for testing this kind of mitigation strategies. And with that, I will open up and finalize my webinar and see if you have any questions. Thank you.
At this time, we will open up the floor for any questions. Again, you can raise your hand in the participant window or write a message in the group chat. So we'll give a few minutes to anyone who wants to ask questions.
Hi, Marianne, this is Jim Rickles. I have a question for you. Very interesting presentation. I think good background and the examples are very good. Exceptional examples. I have a question about that integrator. When you use, I guess, a fourth order undercut it, is it sensitive to the order of the integrator? And what about the effects of maybe measurement noise that you may have in the physical world? On the let's say the ability to reduce the objective functions there, that is compared to uncontrolled with controlled, the effects of the integrating the the processor like theta to theta dot and the effects of noise that it has on the controller. Noise being in the real world, you're going to have sensor noise.
Yes, so that's definitely part of the future work. So integrating the noise measurements and reduction, but we have used different type of wavelet alternatives in order to reduce some of the noise measurements. So that will be another possible application for future research. When we use the Runga kata, so when we use the integration of the neurodynamic model, so that was to determine what will be the optimal values for the replicator dynamics. So the neurodynamic is not part of the controller itself, but it's kind of like the way we're optimizing those values. So we let the control algorithm takes place, look at the performance, and then integrate that into the neurodynamic. So it's not happening in real time. That was one of the questions of the integration, I believe. Right. Some of the things that we do include are part of the constraints. So we do put some constraints on like the maximum actuator control force for each of the actuators to make sure that those are realistic. We'll also look at the drift, what will be the maximum interstory drift, looking at it by code, and looking at ways to do that. So because we're using also semi-active devices, then we know that they're not inputting energy that will be catastrophic, or that require additional studies for stability, like it will be for active control. Okay. Not sure if I'm answering.
Sorry, Marianne. Yeah, that's fine. I appreciate your answer. Thank you.
Okay.
Are there any other questions from anyone?
At this time, there are no more other questions. If you want to give any closing remarks, Dr. Rickles, it's free. You're open to give closing remarks at this time.
Yeah, so Marianne, thank you very much for a very, very interesting presentation, and also to all the participants who participated remotely. You know, our objective of this seminar series is to try to bring exposure to other researchers in the field and create opportunities in collaboration, and at the same time try to educate the general public there about hazards and natural hazard mitigation measures. So hopefully this is partially accomplished today. So I think with that, if everyone could join me in thanking Marianne again, really appreciate Marianne, and I'll follow up with an email to you. And if there's any other questions from the audience, please ask right now. Otherwise, I think we'll go ahead and stop the meeting. Marianne, I think they're kind of quiet today. You explain things very, very well, so I think it's that too. So, okay, well, I guess without further ado, did you have any other comments, Marianne? Or?
No, I'm just saying this is a really exciting field, and I think, when we talk about different games for cooperation or competitive games, I think there's a whole realm of things that we can work on for improving the ways we're mitigating or protecting the infrastructure. So thank you so much for the opportunity to give the webinar today. And I look forward to hearing, following all the other seminar series that we're having for Lehigh University.
Yeah, thank you very much again. And I guess with that, then we'll go ahead and terminate the meeting then.
Yes, thank you, Dr. Rickles. And to anyone who wants more information, you can visit designsafe-ci.org, and there's go to our LEHIGH site, and you can contact us or contact anyone through that organization. Thank you for joining us.